Hello, let's take a look at solving logarithms. And I'm going to show you two different techniques. The first technique, we're going to turn it into an exponential by using the definition of logarithms and solve. And the second technique, we're going to use the one-to-one property, the same base, similar to what we did with exponential functions, like that. So the goal, if you can combine all of the logarithms into a single logarithm on one side of the equals, that's this first technique. So this one only has a single logarithm, so I'm going to isolate it, subtract the 7, divide by the 3. I'm looking at the domain there. I'll talk about that at the end. And now once you've isolated the exponential, turn it into a now that you've isolated, let me pause, rewind. Now that you've isolated the logarithmic function, use the definition to turn it into an exponential. So the base of the natural log is e. So we'll have e to the power of that number on the right equals x. And you want to check to make sure that this still is in the domain. The original logarithm is just, the argument is just x, so the domain is the parent function 0 to infinity, and e to this power is between 0 to infinity. Always good to double check anything you solve, plug it back into the original, make sure the left side is equal to the right side. Here's another example. We've got two logarithms. They are both on the same side, so I'm going to combine them on that side. Again, there's the domain. I'll talk about that at the end. So the arguments get multiplied, and now I've isolated the logarithm, so I'm going to turn it into an exponential. 6 squared equals that quadratic. So now it's just a quadratic. Solve it the way you have solved quadratics all semester. I'm going to set it equal to 0, factor it, and set each factor equal to 0, and then double check the domain. One of the domains is -5 to infinity, the other one is 0 to infinity, so the 0 to infinity overrides, and my only answer is going to be that x equals 4. Double check it by plugging it back in like always, because you still could have done some algebra wrong. Alrighty, next technique. If you can leave a single logarithm on both sides, that's the difference in this technique and the other technique. So I still need to isolate it. So the one on the left has got a coefficient, so I will bring it inside and square it. And then since the bases are the same and I only have a single logarithm, then I can set the arguments equal to each other. And again, it turns into a quadratic. So move everything to one side, set it equal to 0, factor, solve the factors like that. Check the domain. Both of the original logarithms show the domain to be -3 to infinity. So -3 to infinity, and it's a parentheses, so -3 is out. -1 is included in that domain. That would be the answer. Double check like always, or use the other technique. If at the second step I moved one of the logarithms to the left by subtracting and combined it into a single logarithm, that's what the first technique would be. Let's take a look at this next example, a little more complicated. I got 4 logarithms, so I have to combine the 2 on the left, combine the 2 on the right. Again, if you want to move everything to one side, that's the first technique that we looked at. But I'm going to keep them on both sides like that. Once you have a single logarithm on both sides of the equals, same base, set the arguments equal to each other. This is a rational equation, so I'm going to cross multiply the denominator. Now it's a quadratic. We sure love those quadratics, don't we? Move everything to one side, set equal to 0, factor, solve the factors, look at the domain. We got 2 of them that just is the parent function, basic x, 0 to infinity. We got 1 minus x, so that's going to be less than 1 when we get to it. So we've got a domain just between 0 and 1, and so 2/3 is the only value that works for that. Double check.